Assalamualaikum warahmatullahi wabarakatuh. Now we will learn about the basis and dimension. The basis and dimension is the next discussion after we understand about linearly independent and this one and linear combination. So it will be easier for us if we have finished this topic, then continue to basis and dimension, because it will be easier if we can identify and determine where is the linear independent and linear dependence of the factors. So we start from the definition of basis and dimension. The definition of basis is that if we have S is in any vector space where S containing with v1, v2 up to vn is a set of vectors in V, then S is called as a basis for F for the phi if the following conditions hold. We have only two conditions that have to be held. The first is that S has to be linearly independent, and the second one as span of V. And the second one, we discuss about the dimension, where the dimension of a finite dimensional vector space V denoted by dim V is the notation where is dim is standing for the dimension and is divided to be the number of vectors in a basis for phi. So it refers to the number of vectors in the basis for phi. In addition, we divide the zero vector space to have dimension 0. So even the zero factor, we can say that they have a dimension 0. So zero factor space here, it doesn't mean that we have a 0, 0, because it refers to one dimension. So the dimension 0 is really the zero factor space. So we have zero factor space, it's refers to dimension 0. Yeah, difficult to understand maybe, but I will give you the example to help to make it easier to be understood, and then we will start to create this exercise. In this exercise, we have to find the basis and the dimension of vector space V that formed by U1. Okay, I will say that it's the U1 and U2 and it is the U3. So you have to recall our memorize and our discuss in the previous video about the linearly independent, where the linearly independent you have to this equation plus Q3 U3 will be equal to 0. So we can input the number unit of the U1, U2 and U3 to this one. It will be K1 1 1 1 plus K2 1 2 3 and plus K3 1 2 1. It will be equal to 0 0 0. Okay, that's one. And then the next is we will separate in each following the scalar number. So it will be K1 plus K2 plus K3, it will be 0, K1 plus 2, K2 plus 2, K3, it will be 0, and K1 plus 3, K2 plus K3, it will be 0. So what's next? I will call it as the first, the second and the third equation. So we can eliminate by using the first and the second equation, directly, and it will be obtained the result of it is minus K2 and this one minus K3, it will be 0. And then we can operate also from the first equation to the third equation, where it is K1 plus K2 plus k3 will be 0, and k1 plus 3k2 plus k3 to be 0. Okay, then next, directly minus k is 0, and this one is a minus 2k2 will be 0, so k2 it will be 0. We can substitute this one to this equation, so it will get the k3 it will be 0, and k1 it will be 0. So what we obtained now, we have been obtained that this all of this scalar number is linearly dependent, because the scalar number of k1, k2, and k3, all of that is 0. So we can say that this v is linearly independent. And then what about the basic? The basic of this factor, the basis of this factor is v1, u1, or u2, or u3. This is the basis, where v1 equal to 1, 1, 1, equal to 1, 2, 3, and 1, 2, 1, and the dimension of v is, how many dimensions of v here? So dimension of v here is 3. u1, u2, and u3. Okay, that is enough for the first example. In the second example, I will give you about the system of linear equation. So it's more complicated than previous example. So we have the following system of linear equation now, and we have to looking for the basis and the dimension of this system of linear equation. So what first step? Of course, the first step for the matrix here, we have to change this one to be the matrix, and of course we have to write it in the augmented matrix. Okay, if you write the augmented matrix, you can write here 1, 2, minus 1, 2, and 1. Here minus 1, minus 2, 1, 2, and 3, 2, 4, minus 3, 2, 0, and minus 3, minus 6, 2, 0, 3. Then the augmented matrix, we have to input this number, where it is 2, 6, 2, 9. After we got it, we have to continue to the next process, where the next process is a Gaussian elimination. Based on the Gaussian elimination, we have to operate by using the three type 2, type 3, type 1, and type 3. So after we operate the Gaussian elimination, we will get this one. So we will obtain, if you're still confused how to operate by using the Gaussian elimination, please check my previous video. I have explained about how to operate by using Gaussian elimination for the system of linear equation. So after we operate this one, I will make it simpler to show you the obtained the result of after we calculate by using the Gaussian elimination. So this we will get 1, 2, 0, 0, minus 1, and minus 5. Then 0, 0, 1, 0, 0, minus 3, 0, 0, 0, 0, 1, and 2, and the last one, all of this containing with the 0. Okay, this is the result that we will be obtained after we calculate by using the Gaussian elimination. So where we can find the basis here. So the basis will be showed by the pivot element, this one and this one. And we have, I'm sorry, this one. So how many bases we have? So we have 3 bases here. Sorry, this is 1. We have 3 bases here. We have 3 bases, where the bases here containing with this one, I will write the 1 minus 1, 2, 3. It's the first. And the second one is minus 1, 1, minus 3, 2, and the last is 2, 2, 2, and 0. So the basis of this system of linear equation here, and the dimension of this system of linear equation, how many dimensions here? 3, where each dimension containing with 1, minus 1, 2, 3, minus 1, 1, 3, 2, 2, 2, 2, and 0. Okay, that's all for the dimension and basis. So I hope you can I hope you have to check my previous video to help you understand about this video, because it's really correlation, it has the strong correlation, yeah, of course, with the system of linear equation by the Gaussian elimination, and also with the linearly dependence. Okay, thank you.